Thanks for attending my presentation. Today I'm going to talk about our paper, Smart Build Target Batching Service at Google. Here is the roadmap of my talk. Google has a monolithic codebase. There are many services like the Continuous Integration Service, the Online NDE service, and the Production Release service. They all require continuously executing tons of builds per day. However, each worker has a limited allocated memories, which means putting too many targets into a single build might cause out-of-memory errors, and we call those errors OOM. Moreover, each build has a limited number of concurrent executors to use, and each build has an execution deadline, which means putting too many targets into a single build might cause deadline-exceeded errors. A build contains the command name, for example, the build or test or collect coverage, followed by flags. For example, you can specify --jobs, which means the max number of concurrent executors a build can use. There are other flags as well. And finally, you need to specify the build targets. For example, you can specify a hello world target. So internally, Google used Bazel as the command name, flags, and build targets together. A concrete build command would look like this. Specifically, out-of-memory can happen if the target dependency graph for a build is too large to load into the memory, which can happen if you run too many targets in a single build. A deadline-exceeded error can happen if a build could use more concurrent executors than its limit, causing additional actions to queue. We call this kind of deadline-exceeded error type 1 deadline-exceeded error. Another possibility is that a build has a dependent action that must run in sequence, and some intermediate action is long-running, blocking all other executions from executing. And we call this kind of deadline-exceeded errors the type 2 error. In this paper, we mainly focused on eliminating the out-of-memory errors and this type 1 deadline-exceeded error. To avoid out-of-memory errors, we have a memory model, which is a linear regression model that predicts the memory usage in bytes for a given build. The reason we don't use a classification model is that out-of-memory build is extremely rare. And if our model is performing well, which eliminates all the out-of-memory builds, then we don't have any positive examples, which would cause problems for training a model. We use mutual information for feature selection. Mutual information is a measurement of how much a feature contributes to inferencing the label. For example, we found that the command name and some of the flags like cache test result or -- discard analysis cache or the target identity has a very high mutual information in predicting the memory usage of a build, which makes sense. We also use feature cross. For example, we could cross-product the domain of whether a build has this discard analysis cache flag with the tool tag. With feature cross, we can use a linear regression model to learn nonlinear separable problems. To avoid type 1 deadline-exceeded errors, we have an executor occupancy model, which predicts the average number of concurrent executors used by a given build. This is also a linear model. We also use the mutual information for feature selection here. For example, we found that the command name and the CPU architecture, or the max number of concurrent executors a build can use, all of these features has a high mutual information when inferencing the executor occupancy. We also use feature crosses. So now I want to talk about our batching service. The input of our service is a skeleton build flags and a stream of targets, which could be up to tens of millions. So we first sort all the targets in alphabetical order. The reason we do this is that we believe given a set of targets, if those targets have common prefixes, then they are similar and tend to share similar dependencies. Compared to a random set of targets, a set of targets with common prefixes tends to use smaller amount of memories. And then we need to pick a cutoff value for both the memory and occupancy model. And then we pick an initial search point. For example, we could start with this 900 targets. And then we do a binary search with our memory and occupancy model to find a target batch, which at least must contain one target, such that adding an extra target would cause the build to exceed its memory or occupancy cutoff based on our model. And then we would create a build using the build flags and target batch. And finally, we repeatedly searching the rest targets until no more target left. We group the batching size reasons into the following categories. For only one target, batch size reason means the remaining unbatched target list only has a one target, so that we just blindly use that target as a single target batch. The max target's batch size reason means the initial search point would create a valid target batch. All remaining target means the target batch would include all the remaining remaining unbatched targets. Max memory batch size reason means the target batch is created by the binary search with the memory model. The max occupancy batch size reason means the target batch is created by the binary search with the occupancy model. And finally, the memory estimate error batch size reason means we would use the default batch size because the memory model has an RPC error. And similarly, the occupancy estimate error batch size reason means that we would use the default batch size because the occupancy model has an RPC error. Here is our experiment setup. We allocate 13 GB of memory for each build, and each build can use up to 600 concurrent executors. And we have a default build execution deadline of 1.5 hours. In the experiment, we collect 51 million service requests, and our service creates over 102 million builds. We start our binary search at 900 targets. We set our memory cutoff to 7 GB for high priority build, 9 GB for medium priority build, and 10 GB for low priority build. We set a smaller memory cutoff for high priority builds because humans are waiting for those builds, and it's very expensive for a high priority build to run out of memory, and we have to retry. We set our executor occupancy cutoff to 500. This table shows the number of builds, the number of WOMs, and the WOM rate, and the number of deadline exceeded errors, and the deadline exceeded rate for each batch size reason. So looking at the max memory batch size reason, it seems that it has the most absolute number of WOMs, which means the target batch created by our memory model tends to use more memory than other batch size reasons, which is expected. If we don't have the memory model, let's say we have this memory estimation errors, then we can see that we have a higher WOM rate. So in practice, when we don't have our memory model, we used to have a very small fixed target batch size, which decreased our target density, and we have to use more workers to serve those builds. And we can see that the max occupancy batch size reason has more deadline exceeded rate. This is also expected because the target batch created by our occupancy model tends to use more executors. We don't have enough data for the occupancy estimation errors, but in practice, with our occupancy model, we tend to see more deadline exceeded errors. So in general, we have a very low WOM rate and the deadline exceeded rate, which demonstrate that our memory and occupancy model can reduce the WOM and deadline exceeded rates. This table shows the median target batch size, the median execution time in seconds, the median memories in gigabytes, and the median occupancy for each of the batch size reason. We can see that for max memory batch size reason, the median memory usage of a build is around 8.3 gigabytes, which demonstrates the memory model is able to cap the memory usage, and it is useful. So looking at our max occupancy batch size reason, the median executor occupancy is around 521. We can see that a higher executor occupancy typically correlates to a higher execution time, and this demonstrates that our occupancy model is actually useful in capping the average occupancy a build can use. This slide shows our model accuracy. The top two graphs shows our accuracy for the memory model, and the bottom two graphs shows the accuracy for our occupancy model. In the first graph, the x-axis is the memory usage error, which is equal to the actual memory usage minus the predicted memory usage. The y-axis is the build count. So we can see that for all the high priority, medium priority, and low priority builds, the spike is at around 0, which means that our memory model is quite accurate in predicting the memory usage of a build. In the second graph, the x-axis is the actual memory usage in gigabyte, and the y-axis is the build count. We can see that for high priority build, the spike is at around 7 GB. For medium priority build, the spike is around 9 GB, and for low priority build, the spike is around 10 GB, which is expected because we set a 7 GB cutoff for high priority build, 9 GB cutoff for medium priority build, and 10 GB cutoff for our low priority build. In this graph, the x-axis is the occupancy error, which is the actual occupancy usage minus the predicted occupancy usage, and the y-axis is the build count. We can see that the spike is at 0, which means our occupancy model is quite accurate in predicting the occupancy usage of a build. Finally, in this graph, the x-axis is the actual occupancy usage, and the y-axis is the build count. We can see that there's a small bump at around 500 occupancy, which is expected because we have a 500 occupancy cutoff for all the builds. There's also a spike at 0. This is because majority of our build hits the action cache, which doesn't use any executors. So this build has a 0 occupancy usage. So in conclusion, we design a build target batching service that avoids out of memory and deadline exceeded build errors, and we are the first to use the machine learning model model to predict build memory usage and actuator occupancy usage. And finally, we evaluate our service with production data and demonstrate the effectiveness in reducing the out-of-memory and exceeded errors. Feel free to email me for any questions and future collaboration. Thank you.